get people out, but hopefully you can take something away from this. I was part of the exec team for a while, several years ago, and I try and come back every year and give a talk about something that I work with in industry. I understand that the company that I work for did UQCS a little bit dirty this year when it comes to sponsorship. So the company that won't be named going forward, but I do work with Kubernetes pretty much every day in my capacity as a machine learning engineer who doesn't do any machine learning himself. I just facilitate. But we'll get started. So Kubernetes, which I was introduced to by UQCS talk, and sort of had it explained to me in that talk by a friend of mine, and he described it this way. So Kubernetes makes the very hard possible by making the easy stuff also hard. Well, sort of hard, mostly hard. And it's a trade-off that you will make again and again as you move into industry and you solve bigger and harder problems. But I think this pretty much sums it up. The good thing is that you can, at least to begin with, gloss over a lot of the complexity that comes along with Kubernetes, because it's a massive project. But I guess we have to talk about what it is, and I'm going to start big and get more and more detailed as we go. So it's built as a container orchestration system. Containers, some of you may have been exposed to by using Docker, following online tutorials where they've sort of wrapped everything up. Orchestration, making lots of disparate things come together and, in the case of an orchestra, produce beautiful music. And a system, in this case, an environment with actors who interact based on certain rules. So that doesn't help much, but we will get there. First of all, I guess we have to understand what a container is. And there are, again, a bunch of explanations as to what a container is, but we will try and keep it relatively high level. I will point you in the right direction for a better understanding if you want to go deeper. A container is a running instance of an image. Not this kind of image, this kind of image. It's a file format. It's basically a big bundle of files, and the standard is maintained by a group called the Open Container Initiative, and they determine sort of what makes up a container or a container image. A lot of the stuff that they look after was open sourced by a company that you've probably heard of called Docker, who are sort of very much the dominant player from the beginning. And they decided that they wanted something different from the standard. The standard, way back in time, was this idea called a virtual machine, where you pretty much virtualize and create pretend versions of whatever you needed to pretend like your application was running inside an operating system of its own, with all the things that it needed. And this was novel, this was great for its time. And then the folks behind Docker came along and they started to think, what if we had something lighter? What if we had something that was more efficient in the way that it sort of faked out these resources? And they came up with this. This is something that I've been shown many times, and it doesn't really help, but this is sort of your standard explanation of containers versus sort of the virtualization framework. And basically they've stripped out a layer, and they've replaced some layers with other layers, but the crux of it is that they have abused the hell out of a Linux system known as namespacing. And the idea is that you can contain everything in a much lighter way than you could with virtualization. So if you want to understand the deeper sort of nitty-gritty stuff, I'd recommend going back and watching this UQCS talk that I organized many, many years ago and was kindly delivered by Neil, where he will talk about the sort of the underlying stuff, the stuff that goes deep. If you're into operating systems or working out how file systems work and that kind of thing, that's the talk for you. I tend to focus on things at a higher level, just because the minutiae of Linux and architecture and that kind of thing is not really my jam. So I will focus on the higher stuff. If you want the lower stuff, go to Neil. And the recording for that one is quite good. I think that was before we had this fancy setup. But nonetheless, so we're back to this OCI image. And this is the contents. This is a simplified view. But the idea is that there is a manifest, and there are a bunch of compressed, gzipped, tarred file bundles that make up what are called layers. And those layers get expanded and layered on top of one another until they get to the point where you've got basically as much of an operating system as you need. And then there are certain things that you can't really layer in as a file, even as much as the everything is a file is a meme in Linux. There are things that you can't quite shove into those layers. So things like environment variables, things like where your operating system sort of starts, where it goes, what directory it starts in, all goes in the manifest. And the manifest also includes pointers to the layers and hashes of the layers so that it can verify that that layer is what it's after. So that's what a container image is. So once you take that image, you pass it into a program called containerd or similar. It's going to distribute that and they're going to get unpacked and turned into, again, as much of an operating system as you need by a utility called runc. And then you get your running container, for all intents and purposes, a little condensed operating system. And now we're sort of veering back into the user space of the Docker ecosystem. If you've used a Docker image, it was probably built something like this, where you choose a base image, and then again, these commands, pretty much, there are a few exceptions, but most of the commands correspond to the addition of a new layer. So they're changing the file system, they're adding files, removing files, changing the permissions on files, and then layering it on top. And then you've got the metadata, the run, so what you're going to run is in the command, whether you want to expose your sort of operating system in a bottle to the ecosystem outside of it via opening up a port with expose. And you can see here, if you haven't made a Docker image of your own, this syntax at the beginning is sort of, it's like class inheritance sort of ish, where you're pulling in a basis and then you're laying in over the top. So in this case, we're pulling in an image that has the Node JavaScript runtime, and at version 18, and it's the Alpine version. So Alpine is code in this ecosystem for an image that's as small as possible, has a minimal set of tools to get you going, but is missing a lot of the stuff that you might see in an image like Ubuntu 2204 or something like that. So that's how you can make one, and then you run docker builds pointed at this file, and it will create you that OCI image that we were talking about before. So that's a lot of background stuff, and you may be thinking, are we there yet? Can we actually talk about Kubernetes, please? And the answer is yes, but there is more theory, because Kubernetes is basically just one big abstraction over the idea of multiple computers. So the first sort of sub-abstraction of our Kubernetes ecosystem is the node. And the node is an abstraction of a computer, a server sitting in a rack somewhere, your mum's laptop. It doesn't really matter. Anything can be a node in a Kubernetes ecosystem if you try hard enough. And the idea is that if we abstract away the idea that there is one individual computer behind there, we can cut that computer up into subunits. We can, so the way they do that is in terms of abstractions on compute, so CPU, and what they do is they break one core up into milli CPU, so 1,000 units, and then you can use those units and divide them up amongst applications on that server as you see fit. And it will do all the scheduling for you. It will tell you if you have scheduled too much and it won't fit. And so that's your node. And you can run thousands of these sort of subunits. But you also might want to have multiple computers. And for anybody working in industry where computers is your job, typically you're going to have multiple computers somewhere. You're requesting them from Amazon, you're getting them from Azure if you feel that way inclined, or you're running multiple servers on-prem. And the idea is that Kubernetes represents the thing that unites them all. One ship's steering wheel to rule them all. And so there's what they call the control plane is this server that sits in the middle and communicates with all of the other servers and tells them to schedule a job, to kill a pod, to stop things, to run things on a cron schedule. That's its job. It also handles things like auth and role-based access control. So the control plane has a lot of jobs. Thankfully, you don't have to know or understand them all, and you can pick them up piece by piece, as I very much have over the last 2.5 years at a company that shall not be named. So this is just the beginning of the list of APIs that comprise Kubernetes, and they're all versioned, they're all documented, and you can go and probe them as much as you like. You can go and check them out on the Kubernetes website, which is, in my personal experience, a much faster way than using the command line tool, but whatever floats your boat. So there are all these things, but we're going to focus on the very bare bones today, because again, Kubernetes is a massive ecosystem, and we only have an hour. So once we've got our control plane, we've got our individual nodes, this unit, this abstraction that encompasses all of these is called a cluster. And when Neil talked about going from containers to clusters, this is the kind of cluster that he meant, where you're, again, abstracting over the idea. So once you think in terms of a cluster, provided that you don't exceed the resources of that cluster, the combined resources of all those nodes, you never have to think about those nodes ever again until it comes time to upgrade their underlying operating systems, and then heaven help you. So like I mentioned, you can go and get one of these from pretty much anywhere. I'm sure there are more than these. A company that shall not be named uses AWS. In my personal experience, Google Cloud's offering, the Google Kubernetes something, GKE, is the nicest in terms of user experience, but you don't even have to go and fetch nodes and a sort of a managed Kubernetes ecosystem from a cloud provider if you don't want to. For most of the people creating Kubernetes applications, so things to run on these clusters, they're using a tool called Minikube. And Minikube can run on your computer, just like a virtual machine would. It takes up about 20 gigs of space, and it creates this sort of very, very much real feeling, but still artificial Kubernetes environment that you can run applications on, you can play with pods, you can do anything you like with, and it's a lot easier and a lot cheaper than going and getting them from AWS or whomever. So we're not quite done yet. Our next abstraction is the pod. And I don't know, I didn't really think about it, why it was called a pod for a very long time. Someone thought that they were very clever, right? So the Docker image is a whale and multiple whales is a pod, yeah. So that's why it's called a pod. You can have, the idea is that your pod is allocated a portion of your server's resources. You can have multiple containers in a pod, so you might have a main container, and then you might have some sidecar containers doing stuff like providing a database or what have you. So you can have many, but I don't know, for the first, 6 months or so of my interaction with it, I got away with pretending like it was just one. So Kubernetes' job in dealing with these pods is allocating them to nodes. So that's the core job. So it does this via a couple of things. So the resources, you have to have the right resources for it to get allocated, otherwise it'll just sit there pending infinitely. If you want to, you can add additional requirements to your deployments, to your pods, that say it can only go on this type of node. So just say you're training a machine learning model, for instance, and you need it to have a GPU available. So you would say, you can either ask for a GPU, or you can do something called taints and toleration. So you put a taint on a node, and that unless something comes along that is explicitly allowed to override that taint with a toleration, it's going to avoid it. So it'll go somewhere else, or it'll sit pending. So you can reserve resources if you want to. Again, at this sort of level, it's a little bit overkill. But so we've got our clusters with our nodes, and the nodes have pods on them. How do we keep track of what's going where and why? There is another abstraction for this, and it's called namespaces, which is incredibly overused in the technology environment. But in this case, it's basically like, you can think of it like an AWS tag, where you put it on the resource, and then you can filter all of the resources by that tag. So you can say, I want to roll out something to keep track of administration, and I'm going to put it in the admin namespace. You can do that. A lot of tools that come, I'll talk about some of the things that you can use to extend your Kubernetes environment later, but a lot of them have suggest that you use a dedicated namespace for their particular tool. In my experience, breaking things, namespaces are handy because you can delete entire namespaces at a time, and it will go and delete all of the resources in that namespace, and you can start again. And we will come back to this kube system one, because that one is special. So we've covered the theory, and now we're going to talk about how we actually go about interacting with these clusters. So once you've set up a cluster, that process takes about 15 minutes, so I won't do that live for you today, but once you've set up a cluster, it'll have some nodes on it, and you can reach out to it with a tool called kubectl. In my mind, I read it as kubectl. And there is, I believe there is some actual mention in the Kubernetes version updates about an appropriate pronunciation, but you can call it whatever you like. What it is your window into clusters. So you'll have a configuration file, generally, unless you're using Google and they just sort of abstract that away. But you'll have a configuration file that points to your cluster, provided by your provider or your minikube, and then you can do kubectl into that thing. And in this case, we've reached out and we've gotten all of the pods. The -A flag is for all namespaces. So we've gotten, you can see it sort of spans a couple of namespaces there. in my experience. So Kubernetes comes with a default namespace where things will go unless you tell it otherwise. If you follow good practice, like a company that shall not be named, you don't have anything in the default namespace. So when you run kubectl get pods and you don't provide a namespace or -a, you get nothing and you get very confused, potentially repeatedly. Not that this has happened to me. So you can also use kubectl to create resources. This isn't how you will create most of your resources, but it is possible. You can delete resources. You can describe resources. This is incredibly handy when it comes to working out why things have gone terribly wrong. In my experiences, that's mostly things failing on startup or networking problems. But the events at the bottom here will tell you exactly what's happened as it's tried to set up this pod. So here it's found a cached image, and you can see that the messages are coming from something called a kubelet. We'll talk about the kubelet. But yeah, so it started, created a container, and that container is now assumedly running because we haven't been told that it's fallen over. So this is the manifest that I used to create that container running Ubuntu 22.04. I believe it's still running. One of the things you might run into, because I don't often submit things by hand anymore, is that if you don't give it a command and an argument, it will spin up, shut down, think something's gone wrong, spin up, shut down, and it will just go on like that forever. Again, you can theoretically be very confused. But yeah, so in this case, we've spun up a whole Ubuntu operating system, and we can also exec into that pod and use it like a remote machine, should we wish to. So this is the manifest. This is a very minimal manifest. The idea is that this is how you communicate with the APIs provided by Kubernetes. So to create it, you take your pod.yaml and apply it. So this is how you mostly create your resources, because creating them by hand and trying to pass in all of those fields as command line arguments is a bit of a pain. And then you can go and check that it's done what it should. So you can go and, in this case, I've reached out to Minikube and I've said, get pod Ubuntu and give me its current status back in the format output YAML. So there's a lot of crap going on here. That's a lot more than we gave it. But it has filled in the rest with the defaults for a pod. So you can see that it's seems to be reasonably sane. All right, so we've got our manifests. How do we create things that are more complicated? How do we do this in a repeatable fashion so that we're not wondering whether we've constantly applied things or not applied things? So there is a tool called Helm, and Helm is a kind of a cross between a package manager like pip or apt and a templating engine like Ginger in Python. So the idea is that you go to the hub where the Helm charts, as they're called, are stored, and the charts are basically manifests like what we saw before that could or could not have fields to fill in, and those fields are where the templating bit comes in. So this case, we're going to use Carpenter, which is a utility that runs inside of the Kubernetes cluster and sort of extends its functionality. And I'll talk more about it later, but you can go to this hub and fetch the charts. There's a couple of command line arguments and flags. Again, a little bit on the long side. There is another way to do this, which I'll cover if we have time. But the idea is that we're installing from a place, we're filling in the fields, and then we get the completed manifests to create this application called Carpenter and run it on our cluster. So once that process was done, this is going to, you set up Helm on your cluster and it's going to install that for you. Alternatively, if you're a little bit more pedantic, like a company that shall not be named, you will use the Helm templating feature to download all of the manifests with those values filled in, and then apply them using another process that I'll talk about shortly. But let's talk about Carpenter, because I spent, I don't know, 2 or 3 months working very closely with Carpenter, and I think it's a good example of sort of like the power of these clusters to facilitate complicated or large use cases. So Carpenter this is the process we had from before, where Kubernetes is sitting in the middle here, processing the pods, allocating them. When pods drop off and there's space, it'll allocate some more. But what happens if you don't want to wait? What if you have your pods are full, your nodes are full of pods, and you'd really like to run this machine learning training job? The question is, how do you do that when there are no more nodes? So what Carpenter does, and for, as far as I'm aware, only AWS at this stage, is reach out, like it interfaces with the Kubernetes control plane itself and the scheduler, and says, well, is there anything waiting to be allocated? Can I do anything about that? You give it the permission, and it will reach out to AWS and allocate those nodes that you need for you on demand. It adds about 2 to 3 minutes of sort of intervening time while the node is fetched. But once it's fetched and spun up, you can now allocate your job there. And it can do that for sort of any resource requirement that AWS can fulfill, threading the needle between the amount of resources that a particular node has and how many you can ask for is a bit of a complicated problem. But the idea is that you've created this ecosystem that will grow and shrink to solve all of your compute needs, potentially infinitely, up to the availability of nodes from AWS in your region, or even across regions, which is very cool. There are downsides, but it also does the opposite. So once you've run out of jobs to schedule and there's nothing on this particular node, it's going to spin it down and throw it away. So what you've done beforehand, before Carpenter, there was another tool called Cluster Autoscaler. And you could scale, but only between 1 and X number of nodes. So you could never scale to 0. So we spent 3 months chasing this scale to 0 problem. And the savings were on the order of like $500,000 a year. So kind of worth it. And it also gave our machine learning engineers the facility to use the resources of any pod or any node that AWS provided. So if you want a, I don't know, a P48 large with H100s, then you can go and have that. You just have to ask for it. So this, I guess, is a reasonable segue into the idea of a custom resource definition. So we have pods, we have nodes, we have namespaces. These are all objects in the context of a Kubernetes ecosystem. You can also create your own objects, and you do that using these things called custom resource definitions. So in this case, this is a custom resource definition defining the API for something called a provisioner. And the provisioner is the thing that's responsible for adding those nodes and removing those nodes, and making sure that the scheduling was all right. So once you've defined your API, you can then go and say, hey, I want to create one now. and you can say, like in this case, it basically acts as a filter, saying which node types from AWS would you like to provision, or would you like your people to be allowed to provision? How many, what's your global limit on amount of CPUs operating at one time, or how long do you want them to live after they're empty? So all of those fields are defined in the custom resource definition and then passed in, and then that's read by some pods working on the Kubernetes cluster that go and check those things and make sure that all of those rules are being followed. Apologies. So we've come this far. I guess the question is, what is Kubernetes good for? Like, where does it fit? What problems can it help solve? And in my experience, Kubernetes is best for this kind of batch-based machine learning workflows where you're doing a training run, you're storing some training artifacts in an S3 bucket, and then it's shutting down, and it might run a week later or a day later, depending on what you need. So those kind of jobs where it's not critical if a run gets missed. If you've screwed up your cron workflow, that's another resource type that will allow you to run workloads at a specific time, as you would with cron in Linux. And so that's one use case that I found that it's very good for. Things that it can also do other things. So you can serve your web applications from a Kubernetes environment, and it will provide you things like autoscalers, or automatic replication, or if your pod dies, then we'll spin up another one. It has a lot of functionality baked in, but it's also a reasonably complicated ecosystem to debug, because again, there's a lot of things going on. There's a lot of, when you layer these abstractions on one another, it makes it sometimes difficult to debug in a hurry. So if you're serving your application from there and suddenly, I don't know, you've got problems with your ingress, it doesn't necessarily lend itself towards a quick solution. It's a great thing to play around with. Lots and lots of companies are using it. Lots of companies are using it and perhaps shouldn't be. It doesn't really fit their use case or their scale, but they've heard about it, so they're going to use it. But the idea is that you can do a lot, but whether you should or not is sort of something that you may have to find out for yourself. For instance, serving a web application there are tools that are built specifically for that. So Amazon's product ECS does a fantastic job of that. It's relatively cost effective, and allows you to do your auto scaling and everything, but it doesn't have all of this other stuff. It's kind of, Kubernetes is a universal solution that shines in some areas and doesn't necessarily shine in others. So I will leave that there. If you have any questions, let me know. Happy to fill in. But what I would like to do now is show you sort of how easy it is to do that serving. So here I've fetched some manifests. So if we do cat web deployment. So deployment is kind of the next level of abstraction up from a pod. It's going to handle your scaling, and your service is kind of the next level of abstraction up from that. So this is all this application does is return hello world from a web app. but we're going to do something quite cool. So the idea, all right. So we've got that. I've already set up a Kubernetes. Where are we? So I've already set up a Kubernetes cluster with GKE, and it's running. I would do it live for you, but it took about 15 minutes to spin up when I was doing the example, so I won't put you through that. So what I'm going to do here is just apply that, and now we can do kubectl get all. So we can see here we've got a few things already. So there's a service Kubernetes. That's the control plane, I believe. So that was there already. But what's been created is the deployment, the pod associated with that deployment, and something called a replica set. And the replica set is a side effect of using a deployment where you can set it to automatically scale based on some feature, and we will do that. But first, we need to make sure we have so what I've done here, I will so there are two resources in this particular manifest, so you can do that in YAML. And the first one is, we'll start with the service. So the service is a wrapper around the deployment, and it is going to expose it on a particular port. So that's the whole from the pods that it's running in to the Kubernetes environment of the rest of the cluster. And then we're going to already messed up. Fantastic. So what we need is we're going to ask Google Cloud for a public IP address. Oh, no, it already exists. Okay. Okay, so that's our public IP for this. And we have applied both the ingress and the service. So theoretically, if we once again run our kubectl get all, we now have those resources there. Okay, and we want to change it such that. Okay, so what I'm going to do here is run an autoscale command, which is going to change that deployment such that it's going to have a minimum of 10 replicas, a maximum of 15, and the threshold for triggering the spawning up or down of a pod in that group is going to be that the CPU has reached or has dipped below 50% capacity. So we should now have another resource called a horizontal pod autoscaler. And let's have a look at what that looks like. Kubectl describe. Okay, so we've got default information, name, what it's doing. It's got 10 at the moment. We've got events still. we haven't actually triggered anything, and whether I'll actually be able to will be up for debate. But we should, theoretically, now be able to go to this. You can see if we refresh this, it's doing auto scaling, it's taking care of load balancing, and it's being served by a different host every time, which is kind of cool. So you could have a theoretically much more complicated web app, auto scaling, and it's like, what, 2 manifests, 2 lines of G-Cloud do thing, and 4 kubectl commands. And you have a potentially infinitely scalable web application that you can go and serve, which is kind of cool. So, oh wow, that went quickly. I have another couple of things that I can talk about because we've got the time. Once you start doing this, once you start relying on Kubernetes for your sort of daily driver in terms of compute, it becomes a little ridiculous to be manually applying the resources. So they have a process that, I kid you not, is called GitOps. And the idea is that you commit to a Git repository and a service, in this case, Flux CD, continuous deployment, is sitting running on your Kubernetes cluster. It reaches out to your GitHub, GitLab, whatever you want, that address. You've given it the authentication mechanism to get access to it, and it's going to try and apply all of those things, all of the manifests in that repository. It does that by working out what already exists and what's in the set from the Git repo, and sort of does a union on that set, and then goes through and deletes all of the things that didn't exist. So that's sort of once you take this process and you're sort of using it at scale, it's more than just you. That is a reasonable way to do it. There are alternatives. You can do sort of push-based options where you're pushing from your repository to the cluster instead of pulling, but for what it's worth, the differences are very niche. The other, I guess, more advanced concept, and this is what I was talking about in terms of the more controlled, the more pedantic way to do this, is that you can take those manifests from Helm or from the providers, and you can feed them, instead of doing all of that, we have to go back for that here, instead of doing all of this as command line arguments, which is horrifying, what you can do is feed this this original YAML into a programming language called JSONet. And JSONet is a functional programming language with the keyword super, for some reason, that extends JSON to have functions, to have the ability to have, again, they seem like side effects, but basically you feed it in, and it's a much more palatable way of doing that templating than passing in command line arguments. And then you can ask it to spit out the YAML with the values filled in, with the changes, because you might not want all of the stuff in the original schema. So there might be things, and rather than going and hand deleting chunks of YAML, which is always a risk because you never know if it's going to be valid YAML after that, you can use this, and you can filter them out using a functional syntax that looks kind of like JSON with some extra funky operators. And you can add, you pass around information in JSON type objects that can have hidden fields and other kinds of concerning malarkey. But that is, again, sort of a way to advance this process, if you so choose. All right, I think that's it. Managed to finish vaguely on time. Thank you all for coming. And yeah, let me know if you have any questions. Actually, if you want to ask any questions now, otherwise I'm happy to stick around after. Oh, he's got a question.
When should I be using pods versus deployments versus services?
It depends whether you're going to get anything out of the pods. Most of the time, you're going to be building on top of pods anyway. Once you get to the level where you're using this enough. So this is Argo. This is a workflow runner, and it has sort of abstractions on top of them, but they are, at the end of the day, it's sort of a one-to-one mapping between these green bubbles and pods. So you can use pods, but if the deployments and the services are kind of, do you want this thing to be around? Do you want it to be able to scale? Do you want it to be able to do more than just run compute? So it's kind of a touch and go, like experimental sort of process, working out what level you need. But just start small and build. Yep.
How do databases fit into this kind of replication model?
Right.
When there's often like constraints on the need to be consistent with each other.
Yeah. So this is, I mean, a big problem. I guess that's one of those use cases where it doesn't quite fit the Kubernetes model. I mean, you can run a database pod, and it can be your source of truth if you want it to be. Scaling that out is a hard problem, but the solution to that I've seen is that you make your application running on Kubernetes stateless, and then you have your source of truth in a database hosted by one of your big cloud providers, so your GCP, your AWS, RDS or something, and then it fetches information sort of as it needs it, but doesn't rely on it. And if you, again, being stateless is a hard problem. So being like, it adds to the complexity of your application. So again, it might be one of those situations where you think that maybe Kubernetes isn't right for your use case. That being said, most of the other options like ECS are like, they do expect you to be using sort of remote databases that it's not their problem. Yeah.
Does it scale down ECS fast?
That's a good question. I mean, me deploying that tiny web app twice today was my exposure to serving with Kubernetes. Again, we use it as a big, massive compute engine where if things fall over, nobody cares. So the thing that there is it when you with Carpenter, we found that there was this additional delay in fetching nodes. Cluster autoscaler, the thing that came before, was much faster at provisioning nodes and having them, leaving them lying around. So which meant for our machine learning users, these green bubbles popped up faster, which is what they cared about. But they've slowly come to appreciate the value of the sort of, you can have whatever you want, but you might have to wait 2 minutes for it. Yeah. I mean, that was our thinking. So Yeah, I think, I don't know, cluster autoscaler is also very dangerous. One of my early experiences at a company that shall not be named was setting up some new Kubernetes clusters. The new ones were using Carpenter, but the old ones were using cluster autoscaler, and I accidentally deployed 2 instances of cluster autoscaler, and because they're stateless, they were looking at all these nodes, couldn't recognize them in their store, and started killing them at random. So we had disappearing pods for like 2 weeks, and nobody knew what was going on. So that was a lot of fun. Yeah. Any other questions? Yeah? No? Oh, he's getting ready.
I was getting ready.
Okay. Cool, thank you.
Right, well, thanks Nick for giving us that talk on Kubernetes. It's a very, very scary space, but I'm sure you've made it a lot easier. Sorry, I've just realised that we didn't bring our mugs, so I will go down and grab you one of our special edition matte black UQCS mugs that you get for doing the talk. Cough, cough, everyone.
Thank you.
So yeah, hope you enjoy that, so I'll get that for you. But as for everyone else, I guess a couple things. Next week we have a lead-up event to Hackathon, which is How to Hackathon, presented by some of, I guess, our most well-known hackathon attendees of the past, including past winners. So that'd be really cool for you to get to know a bit more about what hackathon is, and obviously our hackathon on the weekend, because that is next week. Yes, oh my god, it's next week. Yeah, so, yeah, Jesus. So if you haven't had got your tickets for that already, they are sold out. So you would need to join the wait list, and we'll see whether we can get some space for you. Otherwise, other than that, we should have pizza out pretty soon. It's not here yet, but yeah, sit tight, and yeah, we'll see you guys in the coming couple weeks.